Okay, we are discussing now about these kinds of questions. It is expected that at least a question of this nature can appear, where you actually suppose that U is this, and you need to find some subspace W that forms a direct sum. Okay, such that F4 is the direct sum of the subspace U together with another subspace W. So what then becomes the answer here? So the solution here to this actually works as follows. Right, so the solution becomes we normally start by letting W, because we must find W. Let
Okay.
W be the subspace. So what we look at here is that there is X here, and there's X, and there's Y. And so what we then suggest is there's X, and therefore we need to just consider one of the X's and one
Mm.
of the Y's. We can decide to consider the second X and sort of alter the first one, right? So we keep this one. That's why I put a 0. Then we've altered the first one. In the same way, we can change the first Y, and then keep the second one, the second Y. Then now this one here, take it to be in F4. Why? Because there are 4 coordinates here. And now these things here, what they are doing, therefore becomes the A and the B are field elements. Okay, these A and the B become field elements,
Mm.
like so. Right, so this is the kind of thing we have. So, um, right, so we have this. So we need to check. What do we check first? So we suspect this. So we need to check that is a subspace. So it must be closed under addition, also scalar multiplication. It must contain the 0 vector. Those 3 properties need to
Oh,
be true. So we check
okay.
if W is a subspace. We check if W is a subspace of F4. Okay, obviously, I'm going to be very brief here. Now, the check is a 3-step check, so we don't expect a lot of even writing. In the long questions, you might find a question like this. Even the multiple choice has appeared for many times, and it is expected that obviously it makes an appearance. Okay, so clearly the 0 vector, the vector that has 4 zeros, as components, 4 component zeros, is of the form having 0 in the second component and 0 in the last component. But A and B are field elements. So it means therefore, obviously from the field, we actually have 0. And therefore, it means that we can have zeros from the field. So it means therefore these guys here are members of this 0 vector is a member of W. That is property number 1. And property number 2 is that if you take 2 vectors from this, their sum is going to be there. So we can have let 2 vectors. What are the 2 vectors? So we can take some 2 vectors from there. We can take the vector U, which is, you can call it anything. All right. You can call it anything, like you can call it U1, 0, U2, 0. Okay. Yeah. And then now you can have another vector V. That is of the nature of this here. So it says V1, for example, 0, V2, 0. Right? So you take these 2 vectors to be members of W. They are actually of the nature of the vectors in the set W. Right. So that now with these 2 vectors, we can add them up. so that u plus v, if you add them now using component-wise addition, we continue. We will have u1 plus v1 would have, if you add the second component, 0 plus 0 is 0. The third component would be u2. Okay, yeah, will be u2 plus v2, and then you would have the last component, 0 plus 0 is 0. And obviously you can see that the sum of the u and the v is of the form, and some non-zero vector, potentially 0, potentially some non-zero vector, and 0. So the sum now is of the nature that has the second and the fourth components as 0. So we continue. We continue. Right, so continuing now would be that, okay, so it's closed under addition. So yeah, W is closed. So yeah, say W is closed. Say that. So we say W full stop here is closed under addition. Okay, this can help in the event of writing a longer proof. For the long questions, if they say find the subspace and need to write a little bit more. Okay, the next thing now is we need two things. We need a vector and a scalar to show that scalar multiplication is also closed, or this set is closed under scalar multiplication. So we can take a constant from the field, and we could also take a vector u of the nature of the vectors in there, and therefore the nature of the vectors would be what, for example, it should be this here. You can take straight A0, B0. Okay. Right. Obviously, this one is of the yeah, it must be a member of W. Essentially, obviously, it is in F4, but most importantly, it is an element in the subspace W. And then now we perform multiplication of CU. Okay, CU would be C multiply each component here. So yeah, we can do that. So it is CA 0, CB 0. Okay, this one is indeed a member of W because it has 0 in the second and the fourth components. Okay, right. So and hence the W is a subspace. So that's W is a subspace. Okay, right. Being a subspace, what else do we need to show to find a subspace? So we found a subspace because it is a subspace. So the question said find a subspace, and here it is. But now we need to show that it is a direct sum. So the summation is not just the summation of two spaces, subspaces, but it is a direct sum. So for the direct sum, we have a couple of things to do. And now I'm going to move to the next page. Right, so moving to the next page, this is what I'm going to do. Right, so on the next page, we have the following. Right, so we need to remember U, because we need to use it. And we need to remember W that we have suggested, because each student will potentially suggest their own W. So you have these ones here, they're actually field elements, but we agree therefore that our W we suggested is of the form A0, B0. Okay, there are a couple of reasons that we have done that. So this here, the A and the B here are field elements, and we have the W like that. So now we need to show this. We need to argue. Okay, right, so we need to argue, we need to prove. Right, we need to argue, we need to prove this. What do we prove? Okay, obviously a proof is a series of arguments. All right, now what do we prove? We need to show that W plus U is actually F4. Okay, how do we go about showing this? Okay, right, so we need to show, but first and foremost, it is a sum here. So Well, point number one, for us to do that, we agree that for any, we take a member of F4, so we can take a B. Some vector B, call it B1, B2, B3, B4. So any four component vector, and this four component vector that is in the F4, right, that is in F4. So, and let us define vectors define okay, we define vectors. Right, so we quickly define the vectors. Right, to define vectors.
7, I will have to go.
Please come again.
At 7, I'll have to go.
Okay, that's fine. I'll let you know. I'll let you go at 7. All right, good. So yeah, let me be very brief. Okay, you define the vectors. So yeah, I'm gonna be very brief now. Okay, so that I can conclude my discussion here. So you define the vectors BW. All right, B1 minus B2. You have 0 here. You have B3 minus B4, 0. Okay, okay, I'll let you go, please, very soon, so that you can be able to do your chores for the day. Right, so we actually take these guys, and these guys are actually in the thing, in W, because they have some zeros. This one is in W because it has some zeros. Okay. Right. Now what you observe is that obviously at this point, thus if you look very carefully, you need to consider as well a BU that is in U. Okay, okay, let me write one more step here. So that is in W, but take a BU. Consider a BU. Ah, okay, having the eraser. So consider a BU. Right, so a B that is a B in W and a B in U. How does a vector in U look like? It has two same components at the beginning and same last components at the end. So you can call these B2, B2, and then you can call these B4, B4, like this, and it is in U. Okay, now BU plus BW is equal to what? Okay, so BU plus BW is actually equal to B. If you add these, you'll get the B1, B2, and therefore, and now this, so that's the B is in U plus W. Okay, right. And also, okay, U plus W, then we make the observation that therefore U plus W can actually be perceived as F4 because of this, but U intersection W is trivial. Is the zero vector? Okay, right. So we take an arbitrary element and argue that it is actually in there, in the 4, and therefore F4 is actually the direct sum of these ones here. All right. So, but what obviously we need to argue that we have the 0, so that it the zero intersection of the two subspaces, so that we have the direct sum with the plus there. Okay. Now I'm gonna quickly, because it's 7, you need to go. This one. All right. This one is a very similar one. Now you need to actually come up with a subspace W over here. What is a subspace W? Right, so here we can argue that now this one here is because now we need to look at for the basis of F5. Right, it helps to look for the basis of F5. What is the basis of F5? Okay, so it says 4 zeros. Okay, 4 zeros. Okay, this 3, that's 4 zeros. Okay, so you have actually that one. Okay, right. So yeah, I'm gonna listen you now. And still need to go. Okay, right. So you have 4 zeros to 4, and then you have 0, 1, and then 3 entries here, and then you have 0, 0, 1, and then 2 zeros. Okay, moving one more, 0, 0, 0. Okay, then 1, 0. Okay, then 0, 0, 0, 0, 1. Okay, yeah, 5 elements, 5, 1, 2, 3, 4, 5. All right, so we argue therefore that this one entry here is gonna be associated with this vector. This one is gonna be associated with this vector. So that these three now, so in other words, this one here has two different, and these ones are just combinations of the different ones. And therefore we consider them as pretty much related to this. So which means that you need to find W. So you actually let W be the same as what? Okay, so W would be like these ones. So it's gonna you can take it to have 0, 0 to accommodate these two guys, and then now you have these ones. So this one, so you can write them anything like A. Okay, because there are three of them. A, B, C. So B, C. Okay, and there are 5 components. Right. So obviously these things here are in F5, such that the A, B, and the C are members of the field. So, but you need to prove the fact that you need to prove that. Okay, so yeah, you have this, and then now you need to prove something very important here always. So, okay, because this one is the span. Okay, you don't need to prove the span. Right, the span would be, there are these vectors that you get here. So there's going to be 0, 0, 2 zeros, and then 1, and then 2 zeros. And then here you'd have 0, 0, and then 0, and then 1, 0. And then 0, 0, 0, 0, and then 1. Okay, so yeah, we spoke about the span. So in other words, this span here, it's this. So you need to just prove linear independence. Need to prove linear independence, and therefore you are done here. All right, so obviously you need to prove linear independence. Okay, I'm just writing that one now so that you can go prove linear independence. Okay, we just obviously are a little bit in a haste here. Okay, prove your independence, but now they might ask you which one is the subspace. So this will be sort of the subspace, because now it's able to get the other ones. This one is going to produce two different components. These components are considered equivalent to these. Okay, next. Now the same question like we saw before, but now it can be broken down into a couple of pieces. Right, a couple of pieces. So you can actually at this point, they're saying find 3 subspaces. Okay, so there's 3 subspaces can be, you can write them as define. Okay, we write with the dots like this. You define W1 to be the span of the following. You can write like this. Okay, so this is also possible, and then you have 4 zeros. 4 zeros. And then what is W2? You define it like this is a span. Okay, and then here you define this one is also the span. Okay, so you'd have 0. Then you have 1. Okay, so okay, I'll explain why these words. Okay, right. So you have the span of this. Okay, W3, you define it, the span. Okay, right. Right. So you have 0, 0. Then you have 1. Okay. Right. And then obviously that's going to be in the third component. So you have this one, yeah, 0, okay, 4, 5, like this. All right. And then, okay, you have these 3 spans, which are the linear combinations like with the A's and the B's like I showed before. And therefore now, in this case, find 3 subspaces. This will be the subspaces. Obviously, if these are subspaces, you can actually go on to show that these are subspaces, and they are actually linearly independent with the vector, with the span of this, because U is spanned by this. U as you can also write U as a span. What is the span? So it is a span like this. Okay, now you look at the X. X, you put 1 here. There's no X 0. There's X 1. There's X 1. There's X, but it has coefficient 2. All right. So that is that. And then there's y. There's no y here. There's y, 1. There's a y here, 1y. There's a coefficient -1 for the y. And then there's no y here. Okay. So you have that this is the case. So this pointer, this will be the span. So you can show that these vectors with this one, if you take the linear combination, they are linearly independent. And therefore, obviously, these ones, if they're linear independent, they generate a 5. So the linear independence is 1, 0, 1, 1, 2, because linear independence is very important when you suggest this, because each student can suggest their own. But at the end of the day, whatever suggestion the student gives must, okay, I'm writing the linear combination. So you have 1, 4 zeros here. Okay, I'm just running. And then this one is D, and then is 0, 1, 3 zeros here. And then this one is actually D. Then you have a 0, 0, and then 1, 0, 0. And then this here is 4 zeros. Thanks for obviously. Okay, so this will be subspaces there. All right, so now, okay, I'm going to make this video available. Now, most importantly, the set of all continuous functions on the interval is a subspace of this. Okay, so they might ask you if this is a subspace there. Okay, the set of all continuous functions is a subspace of this set. And obviously, this one here is only when B0 that it is a subspace of F4. The set of all differentiable relevant functions on R is a subspace of R to the R. The differentiable functions form a subspace of R to R, but the continuous functions form a subspace of this one, 0 to 1. Then the set of all differentiable real valued functions on the interval. This is a subspace if and only if this, okay? Differentiable is only when B0. The set of all subspaces of complex numbers with the limit 0 is a subspace of C infinity. With the limit 0 is a subspace of C infinity. Okay, this one is exactly what we saw. It was just a repeat, okay? So this is exactly what we saw, the W1, W2, W3. I've written them as the spans, like the span of these, the span of that, the span of that, the span of the other, and that is the end of the discussion. Thank you so much. I'm going to make this video available. I understand you need to go. Yeah. Okay, thanks, Mahota. I'll send the video link soon. Okay, thank you. Goodbye.
Thank you.
Okay,
Bye.
thanks. Goodbye.